Hi guys, welcome back. Today we're going to be covering section 21.7, Lewis acids and bases. And we already talked about two other definitions of a acid and a base. Hey Jose, I'll get your attendance in a second. We talked about how Arrhenius acids and the base. What do we remember about Arrhenius acids and bases? What do they both of them donate? The Arrhenius acid and the Arrhenius base both donate. I can tell you that much right now. But what do they donate? If you were to drop an acid into a solution of water, what is the acid going to give off? It's going to donate something. It's going to break something off. What is it? What element do you think we're talking about for Arrhenius acid? A hydrogen. Very good, Diamond. Now, what about the Arrhenius base? If the Arrhenius acid gives up hydrogen, what does the Arrhenius base give up? Oxygen and? Oxygen is correct, but what else also with oxygen? Very good. And what do we call that? Oxygen and hydrogen. When you give it up, what's that ion called? Just O and H. Anybody remember that? High what? High. Huh? Yes, hydroxide. Very good, Ephraim. Hydroxide. That's what we call OH. When it comes to the Arrhenius acid, he gives up hydrogen. When it comes to the Arrhenius base, he's going to give up hydroxide. Excellent. Okay. Now let's see. Let's get this mind working. What about Bronsted-Lowry acids? What do they give away? What do they donate? Yes. Okay. If the Bronsted-Lowry acid gives away hydrogen, what does a Bronsted-Lowry base do? Yes. Very good, Ephraim. He said accepts. Accepts what? Very good. When it comes to Bronsted-Lowry, it's all about the same element. It's all about hydrogen. Acids give away hydrogens. The bases say, come on over, accept hydrogens. Today, we're going to talk about Lewis acids and bases. Now, you got to remember, why did we get that definition of a Bronsted-Lowry acid and a base? Because of what compound that's behind me? Nitrogen. This is NH3. Remember ammonia? Ammonia, we learned, is also a base, but it did not apply to the definition of an Arrhenius base. So Bronsted and Lowry decided to create their own definition that would encompass and include bases like ammonia that didn't have that hydroxide. NH3, ammonia, is a base under the Bronsted-Lowry definition. It's able to accept hydrogens. So we can say, and this picture really sums it all up. The red circle is Arrhenius. It's very specific. You have to have hydrogen or you have to have hydroxide in order to fit that definition. Ammonia was an example of something that was outside of the red circle of Arrhenius, but was inside the green circle, Bronsted-Lowry definition. It fit Bronsted-Lowry, but it did not fit in Arrhenius. What do you think is going to happen with Lewis? Is it going to be able to fit more compounds or less compounds? What do you think it means for that blue circle? More. Why more? Because the circle is bigger. For Arrhenius, it was very small. It was very specific to certain compounds. Bronsted-Lowry picked up the slack where Arrhenius couldn't cover. Lewis is going to pick up even more slack. He's going to include other compounds that doesn't apply to Bronsted-Lowry, that doesn't apply to Arrhenius. Got that? All right, so the introduction says big picture gets bigger. Oscar, are you ready? Oscar, are you ready?
Yeah.
Go ahead.
Ideas in science never stay static. One discovery builds on another one. Another. Our concepts of acids and bases have grown from the fundamental ideas of
Arrhenius?
Arrhenius,
Mm-hmm.
Arrhenius to Bronsted, Lowry to Lewis. Each step adds to understanding of the world around us and makes the bigger picture even bigger.
Very good. Thank you, Oscar. That was excellent reading. Yes, Lewis is going to get more general. Okay, it's going to get even easier to classify under a Lewis acid or a Lewis base definition. Let's check it out. All right, what do you notice just by looking at the picture? What do you notice that that guy is going to be doing?
Giving away hydrogen?
What specifically what? What do you notice? What are these little dots called? The lonely pairs or lone pairs, right? Thanks, Oscar. Great job. Or is that Jeremiah? Jeremiah, you're here with us. I was asking for you.
I'm never mind, miss.
It's okay. Well, you can tell me more about it tomorrow. Hopefully, if you're in class. All right. So it's all going to be about those lonely pairs of electrons that you guys like to talk about, right? They're not lonely pairs. They're lone pairs, but I'll take lonely pairs, okay? Because you do understand what we're trying to talk about. So it all started with, of course, another scientist, Gilbert Lewis. He was able to give us a third theory for acids and bases that was even more general, meaning it was going to be able to cover more compounds than Arrhenius and Bronsted-Lowry. Okay, Irvin, read for me. What does it say about a Lewis acid? Second line towards the end. No, a Lewis acid. Second line. A Lewis acid is a substance. Okay. What was the main part? What is he accepting? Pairs of electrons. The Lewis acid accepts. I always tell my students, well, actually, I always told myself when I was studying this topic, Lewis acid, A for accepts. Lewis acid, A for accepts, right? A in acid is for accepts a pair of electrons. And what's the whole point of accepting electrons? What are you trying to do? What's the goal? What type of bond are you trying to form? Covalent. You are trying to create a covalent bond. A covalent bond, guys, you got to remember, is all about sharing of electrons. If ammonia, as you can see in the picture on top, ammonia has a lone pair of electrons right here on the right side of nitrogen. Now, look at hydrogen. What do we know about hydrogen ions? They're always missing those two dots. They're always missing electrons. They're hungry for electrons. They want to accept these electrons because he knows if he accepts those electrons, we're going to create a bond. And that's what I need as hydrogen. You have electrons, I need electrons, we're going to become friends. You're going to say, hey, Miss Hernandez, I have electrons. Come and bond with me. And I'm going to say, let's do it, America. Let's form this bond. Okay, what about a Lewis base? Okay, so the base will offer out the electrons. You have electrons. You are the Lewis base. Me, as hydrogen, I am the Lewis acid because I want your electrons so that we can both be happy. Right now, I'm unhappy. I don't have electrons. You're happy But why can't we both be happy? No, don't even say it. No, don't even say it. Don't be mean. Okay, so a Lewis acid accepts, a Lewis base donates electrons. Okay, and it's always a pair. It's always two, 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 two. Just like you have two shoes on, we're going to be talking about two electrons. A Lewis acid and base reaction is represented by a transfer of pairs of electrons from the base to the acid. A hydrogen ion, which lacks electrons, will always accept a pair of electrons. So he's always going to be an acid. Hydrogen's always an acid because they're always looking for electrons. They're always looking to accept. Excuse me. Let me drink some water. Hydrogen is an acid under both Bronsted-Lowry and Lewis definitions. Ammonia. Ammonia consists of a nitrogen atom as a central atom with lone pairs of electrons. The reaction between ammonia and hydrogen can be depicted as shown in the figure above. Okay, so we're talking about this picture up here at the very top. We can see that nitrogen is the only compound or the only element that has electrons to share. He's going to offer them to hydrogen, and all of a sudden, you're going to form that covalent bond between nitrogen and hydrogen. Nitrogen, NH3, is going to be my Lewis base. I know, but that's the reading. I forgot to put above. Okay, so nitrogen, NH3, ammonia, will be my Lewis base. Hydrogen will be my Lewis acid because he's accepting those pairs of electrons. All right, take a moment and answer and fill in this blank. I'll give you guys a couple minutes. Get started. Try and answer this question. Everybody should be trying to type some type of answer. I'll read it, but don't answer it. I want somebody to try and type the answer in. A Lewis acid is a substance that, and remember, it's going to be a couple of words. It's not going to be just one word. Is a substance that blank, blank, blank to form a covalent bond. A Lewis base is a substance that blank, blank, blank to form a covalent bond. Finish and fill in the blank. Try it out, guys, please. Oh, I already got 2 people responding. Irvin, are you one of the 2? Why not? Why are you not in the Pear Deck? But why are you not in the Pear Deck? The link is there in the chat. Are you even logged in? Yeah. Well, then log in into the Pear Deck. You have the link. Okay, while you guys are doing that, I'm going to change the attendance for Jeremiah and for Jose. Jose. Got you. Save. Jeremiah. Got you, Jeremiah. Okay, let's look at the answers that you guys provided. I have 4 out of 5 responses. Great job, guys. Very good. A Lewis acid is a substance that accepts a pair of electrons to form a covalent bond. Can donate a pair of electrons. Very good. That's a Lewis base, right? Bases will donate. Lewis acids accept. Just like she said it over here. Very good. What happened to those 2 responses? Come on, guys. Don't be shy. The lone pair on nitrogen is transferred to the hydrogen ion, making NH3 a Lewis base, while H plus is a Lewis acid. That's actually part of the last slide. Some reactions that do not qualify as acid-base reactions under the other definitions do so under the Lewis definition. An example is the reaction between ammonia and boron trifluoride. Okay, try this one out. What can you tell me? Okay, I see two people. Are they on their phone? Are they doing what? Because they're not paying attention here. And I can tell because you're sitting right in front of me. So, if you're looking at this reaction between NH3 and BF3, who is my Lewis acid and who is my Lewis base?
The piece that was accident and
Lewis
Lewis base
Why is that? Why is BF3 the Lewis acid?
because they're donating the
And boron is what?
gravity.
Accepting, adding those electrons to it, right? Very good, girl. Yes, BF3 is my acid because he's accepting those electrons. NH3 is my Lewis base because he's donating. He's giving away those electrons so that we can both be happy, right? To form that covalent bond and the sharing of electrons. And it says it in the paragraph right on the top. Boron trifluoride is the Lewis acid, while ammonia again is the Lewis base. Pay attention to this next statement. As there is no hydrogen ion involved in this reaction, it qualifies as an acid-base reaction only under Lewis definition. So just because we don't have hydrogen, it's still a Lewis base, still a Lewis acid-base reaction because you're still donating electrons to somebody else. Now, let's summarize the table. Irvin, Arrhenius acids and base. What does an Arrhenius acid do according to this little table on the right? What does it donate? Arrhenius acid. What does he donate?
Hydrogen.
Hydrogen. What about an Arrhenius base? What does he donate? Hydroxide. But you're right, it is oxygen and hydrogen. Very good. What about a Bronsted-Lowry acid? He's going to donate hydrogen. What does a Bronsted-Lowry base do?
Hydrogen acceptor.
Hydrogen acceptor. One of them is the acid will give the hydrogen, the base accepts the hydrogen. And then last but not least, we have Lewis. Lewis acids. Electron pairs. A Lewis base. Very good. Very good. Excellent. Did everybody hear that? Irvin, he said that a Lewis acid will accept electron pairs while a Lewis base will donate the electron pairs. Very good, sir. You are correct. Okay. Try this one, everybody. Label the reactants below as Lewis acid or Lewis base. Go, go, go. And you can put LA or LB underneath it, and that way we can see what you mean. LA or LB, so that I know exactly what you mean. Your tools? You can just put LB or LA. LA for Lewis acid, LB for Lewis base. What do you think about this one? Which one is accepting the electrons? Which one is donating electrons? Write it down before we talk about it. Three out of five responses, that's great, but I should really have 5 out of 5. I have 3 people who've answered this question. Where are my other 2 students? Even take a guess. It's a 50-50 chance of getting it right or getting it wrong. Just put LA or LB. LA for Lewis acid or LB for Lewis base. Okay, because I know it. Or you can type it Lewis acid and Lewis base. Irvin, are you done typing or writing? Efrain, you're done? America, you're done? All right, let's check it out. Let's look at our answers. What happened there? Why are you erasing everything? Who did that? I can't read that. Okay. So here we have LB versus LA. Very good. Your Lewis acid accepts the pair. Your Lewis base donates. Very good. Very good. Very good. Awesome. Guys, that's excellent. Except the first one, whoever that was, erasing it. Irvin, was that you?
No, that was the second one.
Oh, okay. Very good, guys.
With the highlighter.
All right, let's watch this video. Doo-doo-doo.
Lewis acids and bases. An American chemist, Lewis, formulated a definition of acids and bases, something that is more inclusive than the Bronsted-Lowry or Arrhenius definitions of acids and bases. So he believed that a Lewis acid was an electron pair acceptor. And something to remember, Lewis acid, same start, acceptor. So an electron pair acceptor is a Lewis acid. A Lewis base is an electron pair donor. For example, for a Lewis acid, BCl3 and AlCl3 can both accept another electron pair, but they don't produce protons. They can't provide protons, so they wouldn't be considered an acid in other definitions. But because they can't accept a pair of electron pair, they are considered acids here. Now, to kind of understand it further, let's think about H plus and NH3. So NH3, I'm going to draw a Lewis dot structure coming from, since we're talking about the Lewis definition of acids and bases. So if I draw this, NH, and I'm going to show that I'm going to form an NH4 positive ion. So that's going to be N, 4 H's. There we go. So this is a reaction that's happening. We have a positive here, and then we have NH3. We have NH3 here. So what we're seeing is that NH3 ammonia acts as a Lewis base because it donates a pair of electrons to the H plus here. So
this reaction is easy to figure out who's the Lewis acid and who's the Lewis base, because do you see any electrons on hydrogen that he can donate? Is there electrons on H that you can donate? No, right? There's no electrons. So it's easy to see that he's going to be the acceptor, the Lewis acid. Ammonia, NH3, we've been working with it a lot. It's already been like 2 examples that he's shown up, and he's always the Lewis base. He's always donating those electrons. Okay, so this example is really easy to predict. Okay, hydrogen's going to be the Lewis acid. He doesn't have any electrons, so he has to accept. NH3 has 1 pair of electrons that it can easily donate to somebody else, making him the Lewis base.
This is the electron pair that it's sharing with this H plus, and that's why it is considered the Lewis base. Now H plus here acts as the Lewis acid because it's accepting the Lewis. It's accepting the electron pair. So this one is donating an electron pair, so it's a Lewis base, and this H plus is accepting the electron pair, and so it's a Lewis acid.
All right, let's check out the next one. It's only a minute long. This one is a little bit harder because they're asking you not only about Lewis acids, but they're also telling you which of the following is considered a Lewis acid but not a Bronsted-Lowry acid. All right. Remember, Bronsted-Lowry acids.
Recognizing
Bronsted-Lowry acids, they are donating hydrogens.
Lewis acids and bases. In this problem, it says which of the following are considered Lewis acids, but not Bronsted-Lowry acids. So we have to go through here and see which ones would fit the Bronsted-Lowry acid definition, and then those are the ones we're going to cross out. This H2O can act as a Bronsted-Lowry acid. So we know that this one is out of the running. NH3 can act as a Bronsted-Lowry base. So NH3 is also out of the running. Now BF3, SnCl4, and FeBr3, all of them can accept another electron pair. And we know that the definition of a Lewis acid is an electron pair acceptor. Why can they accept them? Some of them, BF3, can accept another electron pair, so it can fulfill its octet. Now, tin and iron are both transition metals, and transition metals usually can violate the octet rule because they have a d orbital, and also they have a strong positive charge to them, so that they can access having another electron pair, accepting another electron pair. So C, because it wants to get that octet rule, so C can be a Lewis acid, and Sn and Fe can both be Lewis acids because they can accept electron pairs because they're transition metals. So C, D, and E are answers to this problem.
Okay, let's finish up today's lecture. In summary, we talked about the definition of a Lewis acid and base. We talked about reactions where we have Lewis and acids bases. Oh my God. We talked about reactions of examples of Lewis acids and bases. The review questions. What's the difference between a Lewis acid or base and a Bronsted-Lowry acid or base? 2. What is required to happen in Lewis acid base reactions? And number 3, do all Lewis acid base reactions involve protons? Only number 1 is a little tricky, guys. I don't think you'll have trouble with that one. Or that's the only one I think you'll have trouble with. Sorry.
Base.
Or Lewis acids and bases. Yes. Okay, we're done recording. Let me put the questions in the chat, and then we'll tackle them.